In the first part of this topic, we explored how data gets stored in memory for the byte data type of Java. We understood how negative numbers are encoded using 2's complement form. We also understood the reason behind the choice of 2's complement form, that is to achieve better performance in mathematical operations and less complexity in the hardware circuits. In this episode of Evolving Code, let's explore the byte type further so that you will make better design decisions while picking and using the byte type. Hello and welcome to Evolving Code. My name is Naresha. We know that we can store 256 different values in one byte because 2 to the power 8 is 256. We have seen that we could store from minus 128 up to plus 127. For every number from 1 to 127, we have both positive and negative numbers. That's positive 1, negative 1, positive 2, negative 2, so and so. And 0, we have only 1. There is no negative 0, positive 0. But then 0 will have the most significant bit as 0. So that leaves us one value where the most significant bit is 1 and all other bits are 0, and that gets used for negative 128, thus making 256 possible values. Now that the maximum value or the biggest value what we can represent in a byte is 127, what would happen if we add or increment that 127 variable with 127 by 1? Let's take a look at that. We have a byte type variable number with the value 127, and we have incremented it number plus plus, which means incremented by 1. Let's see what the output is going to be. You see that it's 128. So why it happens can be better explained with the help of the diagram we were using to understand the memory representation. So here you see we have 127, which is encoded like this, which we know from the part 1. 1 is all zeros with the last bit as 1. Now if we add, you will see that 1 plus 1 becomes 0 with the carry 1. Add that 1 plus 1 becomes 0 with the carry 1. Like that it goes all the way till the MSB becomes 1 and all other values become 0. Now which is the number minus 128. So this way we encountered an overflow because one byte cannot represent positive value 128, so it becomes a cycle. Same thing will happen if you subtract 1 from minus 128. It cannot become minus 129, it will become 127. But then you see that we did not get any type of exceptions in the code. It's going to be a silent failure if at all you were expecting an overflow and wanted to convey that to your end users. Better how to manage these overflows with respect to mathematical operations is something we will see in a separate episode when we talk about these arithmetic operations. Previously, when we assigned values to byte variables, we made use of decimal number systems, but you could make use of other number systems. In this case, we have made use of hexadecimal, which starts with the 0x. The radix in hexadecimal is 16, so after 9 you will have A, B, C, D, E, F, and the value F will mean 15. And then we are making use of octal, where we start the number with the 0. So after 7 the value will become 10. That means this value corresponds to number 8. Let's see if it is working as we expected. As we saw, the first F corresponds to value 15 and 10 in octal corresponds to 8 in decimal, and we know that whenever it prints, always it prints in decimal system or the system with the radix 10. Now let's try to assign some values in binary format. Let's start assigning a small binary value here to start with the value 10, which represents 2, and then we are here trying to assign a larger value. So you know that if the 7 bits are 1, it is representing 127. So let's run the program and see what is going to print. So as expected, 10 is 2 and 7 ones make it 127. In this case, since we have many zeros and ones appearing consecutively, it can be a little bit difficult to read this value. So what we can do is, if you want to kind of group 4 at a time, we could insert an underscore. Let's run the code once again. See that the value remains same. So this way to add underscore between the numbers was introduced in Java 7, which we could make use of so that readability of the code is improved. Now let's try to specify a binary number where the most significant bit is 1. So we have seen this already in a previous example. If all 8 bits are 1, it corresponds to -1 in the memory. But let's see what happens here. So let me quickly uncomment that. You will see it's showing an error. If you see, it requires byte, but it's an int. So when we specify a value here, we are not supposed to specify a value in 2's complement form. We will have to represent in a simple binary form. So let's go ahead and fix that and make it -1 with the minus sign. I have fixed my code to make it I can just remove 10 from there to make it 7 bits, and which is 1 with the minus sign here. So that's how it is become -1, and you would see it is showing -1. So here we will have to specify in the way typically normally we use, not in 2's complement form for negative numbers. So that is just how data gets represented internally inside the memory. Just something you need to be aware of. In most cases, your program will receive these data from outside the program. It's possible that your user is feeding the data by keying in some numbers, or it's possible that your program is reading a file stored on your hard disk or SSD to get the data, or your program could be making a database connection and reading the data from the database, or your application could be making a network call and getting the data. All these are the possibilities. Let's say we are getting data from the user and the user is feeding the data through a keyboard. What would happen is user will key in that data, and typically depending on how your keyboard, what type of keyboard you are using and how it is configured, mostly say in a standard US English keyboard, whenever user presses the keys, it will send the corresponding ASCII code, which will then get stored in the buffer, and then that value will be passed on to your program as a string. So for example, I have taken a string variable called input, which is storing the value that we received from the user. What exactly that contains, to check that, let me just debug it, and let's say input, and you would see that it has sent these values. So the 45 ASCII code of negative, then we have 2 and 0, which is 2 is 50, and then we have 0, which is 48. These are the ASCII code that is sent to the program. So what we will do is, now we want to have the data in byte type. So we have to convert this string to byte. So this is possible by making use of an existing method that is already available in the byte byte wrapper class. So we can call byte dot parse byte and pass input to that, and if we run the program, you would see that we are getting minus 20. This is stored in 1 byte, whereas we had 3 bytes of data in the string representation. So once we have the data in numeric type or integer type, we could make use of that to perform say mathematical operations, etc. Most of the time we will receive data in decimal system from the users. That is what people understand better, but just in case this string representation contains data in say octal, hexadecimal, anything like that, we are able to use those information and parse the data correctly. For that we could pass the second argument. Say we want to treat this as an octal value, then we could use radix 8 and run it. It becomes minus 16. Now if you want to use hexadecimal, use the radix as 15, and now the value changes to minus 30. So far we have been dealing with the primitive byte type, but if at all you want to store a byte value in any of the collection types, then we would need an object. Since byte is a primitive type, we would need an instance of the corresponding byte wrapper, which we can make use of. Say we will have a new array list of byte, which we call it as bytes. Then we'll say we want to add byte value. We can say add number, but what happens internally is that the byte gets converted to an instance of byte. You might be thinking of creating a new byte of number like this, but then which still works, but then you'd see that byte, the constructor is deprecated since Java version 9, and we are not supposed to make use of this constructor. What is the reason? Because we could make use of creating many instances of byte. For example, we have a number here 2. You might keep on creating many instances with 2 as the value. The possible values are here from minus 128 to plus 127, but if you have to create thousands or tens of thousands of objects, obviously there will be a lot of duplicate objects which will unnecessarily consume more memory. For that reason, all the constructors have been deprecated. Instead, what we need to do is we can say byte dot value of, let's say 2, or we could just give the number type here. This way you could get the instance of. So if you use byte dot value of number several times, you would get the exact same instance of byte. If you are thinking about how is it possible that we are getting the same instance of byte object, it is because Java is caching all these bytes. So for every possible value of byte type, that is from minus 128 to plus 127, 256 values, Java will already have a cache of these 256 values. Whenever you call byte.value of, it will do a lookup in the cache and get the corresponding value to you. For example, imagine a scenario of you have an array of bytes with say again 10,000 or more than that values. Obviously, you don't have 10,000 possible values of byte. It would be only 256 values. So if you have a 10,000 length array, still we ensure that we are not repeating the byte instances, or it could be very similar situation if we are using any of the collection types instead of array. In this example, I have created two variables of byte type. Then I have an array list of left hand side. Always you could just stick to list. I have a new array list of bytes, and I have added two byte values into that. And if I run the code, you would see it's having a list of two values, 2 and 4. This is how the byte cache would look like. We have an array of byte of length 256. Since there are 256 possible values, the length of the array is 256. The array object will have some header and 256 slots, and each slot will be a reference to an object in the heap, which is an instance of byte type, and each you will have 256 byte objects starting from minus 128 to plus 127 with the 0 coming in between. With this, every time you need a byte object, you will just do a lookup of the object and get that object and use it in the operation or storing something whenever you want. The benefit of using this approach, that is instead of creating object every time and using the cached value, is to have increased performance, because as I said before, the values possible values are very few. You will end up creating many instances of byte with the same repeated value. So with this, by not calling the constructor, we are able to save some compute time, and we would of course trade off some memory in the form of cache to save these byte objects, which will be like a few kilobytes, since the number of objects are about 256, and there is an additional array which is an overhead. Now that you have a very good foundational knowledge about byte, in the next part we will understand how arithmetic operations work, and with that you will be equipped with everything to decide if byte type is the right choice for your situation or it is not. I hope you learned and enjoyed this episode. Thank you for watching, and see you in the next episode.